Hello, my name is Calvin Haynes, and I will be presenting on plastic bonded explosives subjected to confined pressure. A quick definition of a plastic bonded explosive, or PBX, is an explosive material in which explosive powder is bound together in a matrix using small quantities of synthetic polymer. This means that 5 to 10% of the weight will be comprised of the polymer, which means the majority of the explosive will comprise of the explosive powder. PBXs are normally used for explosive materials which are not easily meltable to cast or are otherwise hard to form, and they are mainly used for military purposes and applications such as nuclear weapons and artillery shells. Some of the advantages of PBX, or plastic bonded explosives: they are resistant to accidental detonation if the polymer it receives impact if it is made up of an elastomer, and it can absorb shock. They can also be formed into hard polymers, which can allow the PBX to maintain original shape under severe pressure, and they will not deform and maintain the integrity of the shape of the explosive. They can also be pressed into particular shapes at room temperature, which means they are easily formable, and they can also be machined and done in a safe manner. Under normal circumstances, a plastic bonded explosive is under confinement and pressurization. For example, in an artillery shell, the plastic bonded explosive is subjected to backwards force during launch and a forwards force during impact. The purpose of the testing is to determine the stresses that occur on the plastic bonded explosive during these conditions, as well as any crack formation that may occur. This is to see if the plastic bonded explosive can maintain its engineering performance in which it was designed, and to analyze and predict short and long-term material response to the various loading conditions and temperature conditions in which it is subjected to. One of the main concerns that we look for is the safe use of these plastic bonded explosives. If fracture or yield occurs in these plastic bonded explosives, they may cause unwanted or hazardous ignition, which may prove deadly and injurious to anyone operating near the explosives. The testing specimens will be under confined pressure as well as subjected to uniaxial compressive loadings. These loadings will range from high and low pressure ranges, and they will be applied at various strain rates. The specimens will also be subjected to high and low temperature ranges at these loadings. For this presentation, we will be looking at 3 literature studies. We will be looking at PBX 9502, LX 171, and EDC 37. While all experimental testing parameters vary slightly for each plastic bonded explosive, all experiments were performed for the purpose of looking at the structural integrity of the composites, as well as observance of crack initiation in the material. The first plastic bonded explosive we will be looking at is PBX 9502. It is comprised 95% in weight of triamino trinitrobenzene, which is also known as TATB, and is the explosive powder, and 5% in weight KelF 800 binder, which is the polymer. It is a perforated rectangular plate, and it contains a cavity located in the center. This is the testing specimen. 2 cavity lengths denoted as D will be used in the experiment. Specimen A has a cavity length of 19.05 millimeters, and specimen B has a cavity length of 25.4 millimeters. 2 temperature ranges will be used, and they range from 50 degrees Celsius to negative 20 degrees Celsius. It is under a uniaxial compressive force, and for this experiment, to specimen number 2, which is specimen A, at 500 degrees Celsius will be used because it proved most responsive to the testing. In the experiment, the load was applied and increased, and the displacement of the specimen was observed and graphed in figure A. As you can see, points A, B, C, D, and E all correlate to the contour plots in figure B. The contour plots show the increase of the crack formation that occurs as the load is applied. You can see in point B that the crack begins to form at the top and the bottom of the cavity, and begins to increase in part C. Once the load reaches point D, widespread shear damage begins to occur and cause detrimental damage to the test specimen. It was observed that PBX 9502 exhibits quasi-brittle behavior under uniaxial tension. At negative 20 degrees Celsius, the material is in a relatively brittle state, and a crack can grow even further than it would at a higher temperature. At 50 degrees Celsius, the material is in a rubber-like state, and more resistance to crack growth is provided. Failure did still occur at 50 degrees Celsius, but it was in a much more graceful fashion than it was at the lower temperature. At negative 20 degrees Celsius, the material shattered during failure. Due to the presence of the cavity as well as the shape, tensile crack and shear dominated widespread damage did occur to the material, as well as non-uniform deformation near the cavity was the cause of these failures. As you can see in the graph in the previous slide, tensile crack damage dominates before the max load, and then widespread shear dominated damage occurs after the peak load. This causes the load to go down because the material can no longer support it, resulting in failure. Similar to PBX 9502, LX 171 is also comprised of triamino trinitrobenzene and KLF 800 binder. However, it is comprised of 92.5% in weight of the explosive powder and 7.5% of the binder. It is considered an insensitive high explosive, which means it has a high reaction resistance against impact, friction, elevated temperature, or static discharge. Under these conditions, it will not cause an explosive reaction. For this experiment, it is subjected to 3 axial stress levels, ranging from 270 pounds per square inch gauge to 780 pounds per square inch gauge. It is also subjected to 3 temperatures, 24 degrees Celsius, 50 degrees Celsius, and 70 degrees Celsius. The experiment also ranges the confinement pressure from 0 megapascals in gauge to levels equaling to the applied axial stresses, and which is also known as hydrostatic pressure when the axial stress equals the confinement pressure. And here is the figure of the testing mechanism that will apply the axial stresses and the confinement pressure to the test specimen. The graph on the left shows the data from all the test combinations, ranging from low axial pressure and low temperature to high axial pressure and high temperature. As you can see, the more the confinement pressure is increased equaling to the axial pressure, the less creep rate actually occurs in all cases. While temperature still has an effect on the creep rates are largely a function of the stress rates, which is the difference between the axial stress and the confining stress. At hydrostatic conditions, where the axial stress and the confining stress are equal, small amounts of creep still occur, and this is due to densification of the material as well as presence of voids in the material. The last plastic bonded explosive studied is EDC-37. It is comprised 91% in weight of HMX-NC, which is the explosive powder, and 9% in weight of polyurethane rubber. The dimensions of the test samples are 3.81 centimeters, which is 1.5 inches in length, and 1.9 centimeters, which is 3/4 of an inch in diameter. And all the test samples have a length to diameter ratio of 2. 2 axial pressure ranges were used in the experiment. The low pressure range is from 0.1 to 7 megapascals, and the high pressure range is from 7 to 138 megapascals. Both pressure ranges were subjected to 2 strain rates, which are 0.0005 per second and 0.001 per second. In the graph to the right, axial stress versus strain for 5 pressures is plotted. The upper 3 curves correspond to 3 pressures in the high pressure range, and the lower 2 curves correspond to 2 pressures in the lower pressure range. As you can see, there is a peak in the axial stress in the lower 2 curves indicating work softening occurring. However, in the upper 3 curves, work hardening occurs and allowing to withstand higher stress. It is also observed that surface cracking occurs in the lower pressure range but not in the higher pressure range. Compression in the low pressure ranges produces crack damage, which significantly decreases both the compressive strength and initial modulus of the material, allowing for work softening to occur. Compression in the higher pressure range produces only small changes in these 2 quantities, and work hardening significantly increases the yield strength at these pressures. Possible mechanisms for failure at high pressure include plasticity and fracture of crystalline explosives, as well as the viscous flow of the binder causing debonding and plastic flow. To the right, you can see pictures of the test specimens before and after compression. The top picture is a sample of at the higher pressure range, and the bottom shows a sample at the lower pressure range. In comparing the plastic bonded explosives, PBX 9502 performed the worst. This may be due to the presence of the cavity, which caused cracking and widespread shear damage within the material. The shear damage also caused a load drop, resulting in failure of the component. Further study is needed in order to determine the pressure at which cracking occurs without a cavity. LX 17-1 performed best at hydrostatic pressure and low temperatures, and no crack formations were observed. However, the pressures were not significant enough to cause crack formation, and further study is needed as well. EDC 37 performed the best. Surface crack formations occurred at low temperature ranges, but however, work hardening and increase in yield strength occurred at high pressure ranges. These are the references used for this presentation. Thank you.